The narrative of human discovery has always been characterized by a relentless drive to look beyond the immediate horizon, moving from the shores of ancient continents to the silent, frozen boundaries of our solar system and now, finally, toward the dim red embers of distant suns. In the grand tapestry of the cosmos, as the late Carl Sagan frequently reminded his audience, the Earth exists only as a lonely speck in the great enveloping cosmic dark, a pale blue dot that represents everything we have ever known, loved, or inhabited. This profound realization of terrestrial isolation has long served as the philosophical foundation for our search for life elsewhere, driving a quest to determine whether the life music of the galaxy is a billion different voices or just a faint and reedy tune echoing from a single world. For decades, the search for a second Earth focused on stars similar to our own sun, yet the most significant breakthrough of the 21st century has shifted our gaze toward the galactic boondocks, where small, cool stars known as red dwarfs hold the potential to rewrite the story of habitability. Among these distant outposts, the exoplanet LHS 1140b has emerged not as another pale blue dot, but as a bullseye of liquid potential, a world that challenges our most basic assumptions about where life can thrive and how it might present itself to the observing eye of humanity. To understand the magnitude of what LHS 1140b represents, one must first confront the paradox of its existence as an eyeball planet, a world that stands as a conceptual bridge between the speculative wonders of science fiction and the most rigorous astrophysical data currently being gathered by our most sophisticated instruments. While our planet experiences a cycle of day and night driven by its rotation, LHS 1140b is trapped in a state of tidal locking, perpetually showing only one face to its host star while the other remains shrouded in an eternal, frozen night. This configuration creates a planetary structure that resembles a cosmic eye staring unblinkingly at its sun, with a vast, circular ocean of liquid water serving as the pupil, surrounded by an iris of transition and a global scara of ice. This discovery is a monumental shift in our responsibility toward the preservation and expansion of consciousness, as suggested by physicists like Brian Cox, who argue that if Earth is currently the only island of meaning in a sea of 400 billion suns, the discovery of a stable, nitrogen-rich atmosphere on a world like LHS 1140b represents an opportunity to find a second island of meaning. The search for this world is essentially the search for who we are, a journey 48.8 light-years into the constellation Cetus that forces us to ask if we are prepared to reach across the light-years or if we will remain satisfied as a species confined to a single, fragile marble. The sanctuary that allows LHS 1140b to exist is its parent star, LHS 1140, a red dwarf that serves as the anchor of a red empire vastly more ancient and stable than our own solar system. Red dwarfs, or M dwarfs, are the most populous stellar class in the Milky Way, accounting for nearly 75% of the stars in the galaxy, yet they remain largely invisible to the naked eye due to their low luminosity and cool surface temperatures. While a G-type star like our Sun is a moderate provider that will burn for approximately 10 billion years, red dwarfs like LHS 1140 are the marathon runners of the universe, possessing the ability to burn for trillions of years due to their slow consumption of hydrogen fuel. This longevity is the primary factor that increases the habitability of M-dwarf planets, as it provides an extended period for the slow and complex process of biogenesis to occur. However, this stability often comes at a price, as most red dwarfs are notorious for their violent youth, characterized by intense flares of X-rays and ultraviolet radiation that can strip the atmospheres from nearby planets, leaving them as airless, barren rocks. LHS 1140 is a remarkable outlier in this regard, identified by astronomers as a quiet star that lacks the frequent, destructive flare events observed in other nearby systems like TRAPPIST-1 or Proxima Centauri. This stellar tranquility is the first pillar of LHS 1140b's habitability, suggesting that the planet has been able to preserve its atmosphere and water over its 5 billion-year history because its sun is a gentle provider rather than a volatile tyrant. The discovery of this world is a testament to the meticulous work of generations of astronomers who tracked the high proper motion stars that seem to race across the sky relative to the distant cosmic background. The designation LHS refers to the Lutten half-second catalogue, a massive astronomical effort led by the Dutch-American astronomer Willem Jacob Lutten, who spent his career identifying stars that moved faster than 0.5 arcseconds per year. Lutten, who remarkably lost the sight in one eye early in his career, used a blink microscope to compare photographic plates taken decades apart, discovering hundreds of thousands of nearby stars and white dwarfs. It was his labor that allowed the M-Earth project in 2017 to identify LHS 1140 as a prime target for the transit method, which detects the minute dip in a star's brightness as a planet passes in front of it. Following the initial detection, researchers used the HARP spectrograph to measure the radial velocity of the star, detecting the subtle wobble caused by the planet's gravitational pull. This dual detection is exceptionally rare for potentially habitable exoplanets and allowed scientists to calculate the mass and radius of LHS 1140b with a level of precision that revealed a world unlike anything found in our own solar system. This precision transformed the planet from a mere point of data into a super-Earth, a massive rocky world with a density that suggested it was either a mini Neptune or, more enticingly, a water world composed of a fundamental mix of rock and iron joined by a massive abundance of liquid water. Scaling the giant that is LHS 1140b reveals an environment where the laws of physics create a world of staggering proportions and crushing forces. With a radius 1.73 times that of Earth and a mass roughly 5.6 times greater, the planet possesses a surface gravity that would be devastating for a human traveler, reaching approximately 2.41 times the gravity of Earth. On this world, a person would weigh more than twice their terrestrial weight, their bones subjected to a constant, heavy pressure that makes every movement a monumental effort. Yet this high gravity is also the planet's greatest asset, as it provides the strength necessary to hold onto a thick, secondary atmosphere against the solar winds of its red dwarf host. The density of the planet, estimated at 5,963 kilograms per cubic meter, is roughly 108% of Earth's density, which is actually lower than what would be expected for a purely rocky planet of this mass. The physics of internal pressure dictate that scaled-up versions of Earth should be much denser. Therefore, the low density of LHS 1140b strongly suggests that 10 to 20% of its mass is composed of water. This is a staggering amount of liquid, far exceeding the 0.02% found in Earth's oceans, and implies a world where water is not just a surface layer but a geological driver, perhaps existing in a mantle that transitions from liquid to exotic, high-pressure ice phases like Ice 7 before reaching a rocky core. The phenomenon of tidal locking is the primary architect of the eyeball planet's unique geography, a process driven by the immense gravitational forces exerted by the host star at such a close orbital distance. Because LHS 1140b orbits at less than 10% of the Earth-Sun distance, the gravitational gradient across its diameter is so extreme that internal friction has acted as a brake on the planet's rotation over millions of years. As explained by astrophysicists like Neil deGrasse Tyson, energy is dissipated through the deformation of the planet's structure until its rotation period perfectly matches its orbital period, reaching a state of minimum energy where the planet perpetually shows one face to the star. This results in a world of absolute geographic permanence, where the weather patterns, temperature gradients, and environmental zones never change. On the night side, the temperature is low enough to potentially freeze the atmosphere itself, creating a wasteland of nitrogen ice that has never seen the light of a sun. However, the presence of a substantial atmosphere acts as a giant conveyor belt, moving heat from the day side to the night side and preventing the total collapse of the air. This heat transport is what allows for the existence of the substellar ocean, a 4,000-kilometer-wide pupil of liquid water centered at the point where the red sun never moves from its zenith. If one were to stand on the shoreline of the substellar ocean, the environment would be both familiar and utterly alien, characterized by a sky that is a deep, dark purple or brown, dominated by a massive red sun that appears several times larger than the sun does from Earth. Recent climate simulations, bolstered by data from the James Webb Space Telescope, suggest that this region could have surface temperatures as high as 20 degrees Celsius, creating a balmy, spring-like environment. However, the light would be shifted heavily toward the infrared spectrum, and the vegetation, if it existed, would likely be black or dark purple to absorb as many photons as possible from the weak starlight. This ocean is not a shallow sea but a deep, pressurized abyss hundreds of kilometers in depth, where the water at the bottom is compressed into solid, hot ice despite the high temperature. Surrounding this liquid pupil is the iris, a transition zone where massive glaciers flow from the frozen global ice shell into the sea, creating a shoreline of ice and water that stretches for thousands of miles. Because there is no day-night cycle, the weather is incredibly stable, with a permanent storm system perhaps existing at the center where warm air is constantly rising into the atmosphere. The quest to confirm the habitability of this world reached a critical climax in mid-2024 through the observations of the James Webb Space Telescope, which provided the first tantalizing evidence of a nitrogen-rich atmosphere. Using the NIRIS instrument to perform transmission spectroscopy, an international team led by Charles Cadieux measured the starlight passing through the planet's atmosphere during a transit, looking for the chemical fingerprints that would identify the air. The results were a massive victory for exoplanetary science, as they strongly excluded the mini-Neptune scenario and confirmed that the planet is a solid-surface super-Earth. The absence of hydrogen in the atmosphere suggests a secondary atmosphere formed after the planet's birth, much like Earth's, which is a fundamental requirement for the evolution of biology. Furthermore, the detection of nitrogen is a major milestone, as nitrogen provides the atmospheric pressure necessary to keep water in a liquid state and is a critical building block for life. While the researchers emphasize that these results are tentative and require several more years of observation to rule out stellar contamination, the presence of nitrogen on a temperate exoplanet suggests that LHS 1140b has successfully retained its air for billions of years. The potential habitability of LHS 1140b is also governed by what scientists call the albedo paradox, a realization that being in the Goldilocks zone does not automatically guarantee warmth. At its current orbital distance, the planet receives only about 43% of the energy flux that Earth receives from the Sun, meaning that without a greenhouse effect, it would be a frozen desert with a surface temperature of -47 degrees Celsius. The key to its liquid ocean is the thickness of its atmosphere and the specific nature of red dwarf light, which is primarily infrared. Unlike visible light from our sun, infrared radiation is absorbed more effectively by ice and snow, meaning the ice albedo feedback that would freeze a planet around a sun-like star is significantly weaker around a red dwarf. This allows the dark liquid water at the substellar point to absorb enough energy to overcome the reflectivity of the surrounding ice, maintaining the eyeball ocean in a state of delicate equilibrium. Calculations suggest that if the planet has a greenhouse effect just twice as strong as Earth's, which is likely given its high gravity and atmospheric retention, the surface temperature would rise to a comfortable 23 degrees Celsius, making it a true oasis in the cosmic dark. Comparing LHS 1140b to other famous candidates for life, such as the TRAPPIST-1 system, reveals a shifting momentum in the scientific community toward the super-Earth in Cetus as the most promising target for future study. While TRAPPIST-1 has 7 Earth-sized planets, early data from the James Webb Space Telescope has been disappointing, suggesting that the inner planets may have no atmospheres or water due to the intense flare activity of their host star. In contrast, LHS 1140 is a quiet and stable star, providing a much safer environment for its planets to hold onto their volatile chemicals over geological time. Furthermore, LHS 1140b's larger size and higher gravity make it a more mature candidate for life, as it possesses more internal heat to drive the geological activity, such as volcanism, that is necessary to replenish an atmosphere. As Jason Dittman, the discoverer of the planet, has stated, it is currently the most enticing target because it offers the clearest signal for our telescopes to read, allowing us to move from guessing about water to actually seeing the reflections of a distant sea. The ultimate reality check in this journey of discovery is the incomprehensible distance that separates us from LHS 1140b, a 48.8 light-year void that challenges the limits of human technology and imagination. This distance represents roughly 460 trillion kilometers, a span so large that a radio message sent today would take nearly 50 years to arrive, and a reply would not return for another century. Traveling at its current speed, the Voyager 1 spacecraft would take approximately 860,000 years to reach the system, a voyage that exceeds the entire history of the human species. This reality means that LHS 1140b is not a home we can inhabit in the near future, but rather a home for our data and a destination for our technological aspirations. Proposals like Breakthrough Starshot, which aim to send tiny, laser-propelled probes at 20% the speed of light, could theoretically reach the system in 240 years. A multi-generational journey that would require global commitment to exploration and a fundamental shift in how we view the longevity of our civilization. Point 1 as we look toward the next decade. The narrative of LHS 1140b is moving into a phase of characterization, where the James Webb Space Telescope and upcoming ground-based, extremely large telescopes will focus on confirming the chemical composition of the atmosphere and searching for biosignatures. The high-priority schedule of observations aims to definitively prove the existence of nitrogen and search for carbon dioxide, which acts as the planet's thermostat. If we can detect oxygen, ozone, or methane in the eyeball ocean, it would be the most significant discovery in human history, finally answering the question of whether we are alone in the universe. We are the first generation in history that can do more than just speculate about life on other worlds. We have the instruments to check, and LHS 1140b is our best chance to hear a second voice in the cosmic fugue. Stephen Hawking often reminded us to look up at the stars and not down at our feet, arguing that our curiosity about these distant worlds is not just romantic, but a practical pursuit of human continuity. The eyeball planet stands as a testament to the unblinking gaze of the universe, a world that stares back at its star with an eye of liquid water, inviting us to contemplate our own place in the great cosmic dark. The discovery of such a world challenges our terrestrial-centric view of habitability and forces us to recognize that life may exist in configurations we never previously imagined. Whether LHS 1140b is a barren ice world or a thriving sanctuary of biological complexity, it remains the premier candidate for the most important scientific investigation of our time. The universe has provided us with a target that is close enough to study but distant enough to require our greatest efforts to reach, a bridge between our lonely pale blue dot and the potential for a secondary genesis. In the end, the search for life on LHS 1140b is a search for ourselves, a drive to understand if the spark of consciousness is a galactic fluke or a common property of the universe that thrives wherever the conditions are just right. Our understanding of the internal structure of LHS 1140b continues to evolve as more precise measurements of its mass and radius are integrated into complex planetary models. These models must account for the fact that a world with such high mass and relatively low density cannot be explained by a rocky composition alone. If the planet were a purely rocky world, its radius would be significantly smaller, around 1.4 times that of Earth, but the observed radius of 1.73 indicates a thick envelope of less dense materials. This has led to the consensus that LHS 1140b is an ocean world, where the water is not merely a thin film on the surface but a significant portion of the planet's bulk. In such a scenario, the water layer could be hundreds of kilometers deep, exerting enough pressure at its base to form a layer of high-pressure ice that isolates the liquid ocean from the silicate mantle. This isolation could have profound implications for the chemistry of the ocean, as it would prevent the direct interaction between water and rock that is believed to be essential for the origin of life on Earth. However, tidal heating driven by the gravitational interaction with the host star could provide a source of energy that maintains the liquid state and drives geological activity, potentially through cryovolcanic geysers that erupt through the ice shell. The scientific reality of LHS 1140b is also defined by its location at the outer edge of the host star's conservative habitable zone, a region where the balance between stellar energy and atmospheric greenhouse warming is most critical. Being at the outer edge means the planet receives just enough energy to maintain surface liquid water if it has a strong greenhouse effect, primarily driven by carbon dioxide and nitrogen. If the atmosphere were too thin, the planet would be a frozen snowball. If it were too thick with hydrogen, it would be a broiling mini-Neptune with no solid surface. The recent JWST results showing a high mean molecular weight atmosphere suggest that the planet has found the perfect middle ground, a secondary atmosphere that has survived the star's active youth and now provides the pressure necessary for stability. This makes LHS 1140b the highest priority target for atmospheric retention studies, as it allows us to test our models of how atmospheres evolve around the most common stars in the galaxy. The future exploration of the LHS 1140 system will likely involve a multi-generational effort that combines the power of space-based observatories with the ambitious goals of interstellar probe missions. In the short term, the JWST will continue to monitor the planet's transits, looking for the telltale signs of life's presence in the form of atmospheric gases. In the medium term, ground-based telescopes like the Giant Magellan Telescope will provide the high-resolution imaging needed to resolve the surface features of the eyeball ocean. And in the long term, missions like Breakthrough Starshot could finally bridge the 48 light-year gap, sending a fleet of tiny probes to capture the first close-up images of an alien sea. This progress is a race against time and a testament to the enduring human spirit of exploration, as we strive to ensure that the meaning we have found on Earth survives and thrives among the stars. The eyeball planet stares back at us, a silent witness to our progress and a reminder that the universe is a place of infinite possibility for those with the courage to look. Point 1. The philosophical implications of discovering a habitable world like LHS 1140b extend far beyond the realm of astrophysics, touching on our understanding of our own purpose and the fragility of our existence. If we find that life is common around red dwarf stars, it would mean that the galaxy is likely teeming with millions of habitable worlds, each with its own unique history and potential. This would fundamentally change our relationship with the cosmos, moving us from a state of lonely isolation to being part of a vast, biological community. Conversely, if we find that LHS 1140b is a sterile wasteland despite its ideal conditions, it would highlight the incredible rarity and preciousness of the life we have on Earth. In either case, the search for the eyeball planet is a moral imperative, a way to fulfill our responsibility as the only known species capable of understanding the universe and our place within it. As we turn our telescopes towards Cetus, we are not just looking for another world, we are looking for future. Point 1. In conclusion, the story of LHS 1140b is one of the most compelling narratives in modern science, a journey from the archival work of Willem Lutten to the cutting-edge spectra of the James Webb Space Telescope. It is a world of extremes, where a massive red sun hangs perpetually over a 4,000-kilometer ocean of liquid water, surrounded by a global shell of ice and held in place by titanic gravity. It is a world that has preserved its atmosphere over 5 billion years of stellar history, offering us our best chance yet to find a secondary genesis and answer the question of our own solitude. The 48 light-year gap is a monumental challenge, but it is also a call to action for a species that has always been defined by its need to explore. LHS 1140b is the unblinking eye of the cosmos, a world that stares back at its star and at us, waiting for the day when we finally reach across the dark to say that we are here.